In this example, we look at the problem with the heat exchanger where the temperature of the hot fluid has a relation with the flow rate of the cold fluid, which is given by this transfer function -2/20s plus 1, and there is a time delay of 4 units. Typically, the hot fluid temperature is measured at the outlet of the heat exchanger, and there is a time delay between this change in the cold liquid flow and the change in the hot liquid temperature. Okay. So initially the flow rate of the cold liquid is at 20, and at some point it's brought back to 16 liter per minute, and then continued that for 2 hours and then brought back to this 20 liter per minute. So initially the temperature of the hot liquid is 135 degree centigrade. It asks you what will be the maximum temperature of the hot fluid, and if there is an alarm which is meant to set off at 140 degree centigrade when the alarm will sound. Okay. Now for doing this, let's look at the expression for this Fc prime. So the Fc prime T will be Fc naught. So we'll have, if you subtract 20 from 16, it will be -4. So Fc is a pulse with m -4 and T equals, so it remained there at value 16 for 120 minutes, 2 hours. So T equals 120. So we'll have Fc prime S to be -4/S plus 4/S minus 120S. Okay. Now if we look at this, now plug in the values for this FCS in this equation, we'll have TH prime S will be -2/20S plus 1 for S So if further simplify this, it will be 4 times 2, 8/S 20S plus 1 exponential -4S positive negative 8/S 20S plus 1 negative. Now you see 120 and 4, it will be 24S. Okay. Now if we take the inverse Laplace transform, the expression for TH prime T will be again 1 minus E. You know that it will be e to the power -t minus whatever is the delay over this tau. Now this is -8 1 minus e to the power -t minus this now 124 over this tau 20. If you look at the transfer function here, you can find out when the flow rate goes down, because of the negative gain, temperature will go up, and you can find out that the temperature will be somewhere there, it will reach the maximum. Now I'm saying somewhere there because there is a time delay. Well, because of the time delay of 4 units here, it will start right up to this time delay and go all the way to again time after time delay, and then it will come back. Okay. So do note that there is a time delay there in the model itself. So that's why you're starting after the time delay and going beyond the time delay before the change in the other direction takes place. Okay. Now you can find out from this expression that T prime H will be maximum when this part is 0, right? T prime H will be maximum and this part is 0. And this part is 0 when it approaches this point. Okay. So now to be mathematically correct, we'll write it when the time approaches 124 negative, meaning just before this 124, because we said that at 124 it will start to move again. Okay, so we can say that this T at minus 2 is mathematically correct. Okay, so then for that case, T prime HT will be minus, okay, and then plug in that equation there. It will be, this value is 135 plus 8 so this will be 24 here, because before that it's 0, so that's 0 anyway. So we'll have, if we look at this value, so this value is very close to 0, so we'll have 134 plus 8, which is 143 degree centigrade. That's our TH max. Okay. Now let's look at the second part. If there is an alarm and alarm sets up at 140, what time the alarm will set? Okay. Now for this case, look at this equation again. You will have the maximum values goes to 143, and the alarm will set off before 143 at 140. So that will happen before it reaches this point, meaning that will happen before T goes beyond 120. Okay, so we can say that the alarm set off at T alarm, which is less than 124. Okay, you know that will happen before it reaches the maximum. Okay, so for this case, we'll have, again it will be T. So if we have this alarm at 140, we'll have 135 plus, only you'll have this part, T minus 4 over 20, and we know how to solve this. So we'll find this T alarm to be 23.6 minutes. Now where is one term was missing here, that we need an additional term there to represent the time delay for this case, because before time equals 4, that term is also 0. So it will not change until time equals 4. Okay, so we have that alarm set time to be 23.6 minutes. Okay, there is a third part there. If so, it asks when the temperature will go back to 1 degree centigrade of initial value. So it's 135, it goes within 1 degree centigrade of this initial value. So if within 1 degree, meaning that we're looking for some value of 136 degrees. Okay, so it says when 36 after reaching maximum. Okay, so for this case, again we look at this. So we'll have that will happen after t equals 120 or 124. So we'll have to use this entire term. So for this case, we'll have THT will be T, and we'll have this THT is 136 plus 8 Know that we don't need this term because we are considering this will happen before after time equals 124. So for all this t is greater than 124, so this will be 1, and the second term is so now again if we want to solve it, we'll have that okay, there is no analytical solution for this case. If we try to take log, that won't work. We need a numerical solution. However, this part we're talking about some t which is much greater than even 4 and which is greater than 124. So if you plug in the value here, you'll find that this value will be very close to 0. And if you just simply solve it, you will get t equals, so this term will be 0, this 8 and negative will get cancels out. So on the left hand side we'll have 1 degree, on the right hand side we'll have only this negative, negative, positive, exponential negative t minus 124 over 20, and you solve it, you'll get something like 166, which is minute. So it will be 2 hours 44 minutes. Meaning that the value is brought back to this value 20 after 2 hours. It will take another 44 minutes for the temperature to go within 1 degree centigrade of the initial value.